Hi, so thank you everyone for coming today. I'm happy to see you coming for a sixth webinar from this free webinar series. The topic today is heat treatment for steel alloys. So we have received new ideas from some of you, and we thank you for that. Heat treatment was actually one of the high topic on the list that you have requested, so we are addressing this topic today. Last point before we start, as mentioned in email, we want this webinar to be interactive, so please do not hesitate to use the chat feature to ask a question. Since I have muted everybody, we'll monitor the questions and try to answer on the go. Today we will have an overview of the heat treatment, focusing on optimization, quenching, tempering, and carburizing for steel alloys. We will not address aluminum and titanium heat treatment today. That will be part of a separate webinar if there is some interest in that. Also, for more hands-on and focused heat treatment processes, we'll ask you to refer to our training portfolio. So please contact us should you have any interest on this. Now, I'll let Sergio Rodriguez, our technical support engineer, lead this webinar. Sergio, go ahead.
Okay, thanks, Nico. Good morning, everybody. As Nicolas said, we are going to review today heat treatment only for steel alloys. The content of the webinar will be a quick introduction on the different heat treatments we can simulate in FORGE or SIMHEAT. I'll start talking about the TTL Diagram generator. I get a lot of questions about this. I'm going to review all the capabilities of this tool. It's included with FORGE. Everybody can use it. And then I will start talking about the characteristic points of the quenching templates, carburizing templates, and tempering templates. I'll talk about the characteristics that are unique for these templates. So I'm going to, for this webinar, I'm assuming everybody knows how to run basic simulations. If you have any additional questions that are not answered in this webinar, please contact us to our support email, and we will answer those questions. Again, I'm going to talk mainly about the characteristic points of each template. Okay, so as a quick introduction, I'm going to talk about the main heat treatments we can simulate in FORGE or SIMHEAT. For heating, we can do standard authorizations or inductions. If you are interested in inductions, please review the first webinar we did. It should be available to watch again. We did a complete review on that, so that's covered. Optimization, we will mention it today. Chemical and element diffusion, this is used to increase the hardness in the surface or external surface of the parts. There are two main options, carburizing and nitriding. Nitriding is still in development, so we will focus in carburizing today. If you need to run a nitriding simulation, you can contact our support and we will tell you if we are ready to run that simulation or not. It's still in development. And then for cooling, we have quenching. Everybody is familiar with what a quenching is. We will do a quick review later. Yeah, so with that, let's keep moving. Normally, these heat treatments are correlated. We have some examples here. Normally, right after we heat the part, we cool it with a quenching. I'm not going to get into details about how heat treatment works because we don't have a lot of time, and the main focus today is to review the tools we have in the simulation. For carburizing, for nitriding, again, it's under development, so we are still working on it. Normally, we will choose different heat treatments depending on what we want to achieve. If we want to achieve high values for hardness in the external surface only, normally we will go with carburizing. If we want to achieve it in the whole part, normally we'll go with volume hardness. This is just some examples of the different hardness we can get. And now I have to introduce the concept of TTT and CCT curves. Normally in heat treatments, we're going to be interested in the microstructure phases of our steel. In order to simulate this in Forge, we are going to need TTT data. TTT data is just the curves, time temperature transformation curves that most of us are familiar with. These curves determine when phases transformation start and end. Well, they are generated by transformation percentage versus time measurements with isothermal transformations, but we're not going to get into details. I just want to make sure everybody understands that to simulate phase transformation in Forge, we need the TTT diagram, a characteristic for that material. If you have this information, we will be able to simulate microstructure phases. If you have problems importing this information in Forge, please contact us and we will help you to import it in Forge. Another curve associated with the TTT is the CCT, continuous cooling transformation. This curve on the right, bottom right, represents the phase changes for different cooling rates. We have the different letters for the different phases in our steel here, and each of these curves is a cooling rate. We will see the phase transformation we obtain based on the cooling rate. The important thing about CCT curves is that they can be used to optimize the TTT data we have. This is done in the diagram generator that I've mentioned before. We are going to review it next. The TTT and CCT diagram generator. You can access this tool from the home window when you open FORGE or SIMHEAT. It's on the bottom left, TTT and CCT diagram generator. This tool is meant to be used with microalloy steels only. So it's possible if you have a high percentage for any element that you get a warning message saying that the tool is not calibrated for those values. If that's the case, you shouldn't use this. You will get an error message right away saying that the tool is not meant for that percentage. Okay, so here first we have the open section to import existing TTT diagrams. Clicking here will take us to the default TTT material files in Forge. These can be used as a template. So if you want to start importing your own TTT curves and you are not sure about the structure, please click here. You will be automatically taken to the default folder and you can use those materials as template. Okay, if we don't have the TTT diagram and we're creating one from scratch, we don't need to use the open section. What we need to create the TTT diagram is the chemical composition entered here for the microalloy steel. Also, we'll need the grain size, the initial grain size. After we have entered grain size and chemical composition, a name, otherwise you won't be allowed to export the material, you will get a green light in here, and this means you will be able to export your TTT information. This is used to remove the data entered, and this pencil here, it's used to modify the characteristic temperatures of our TTT curves. This tool uses a model, and sometimes if we have the real values for these characteristic temperatures, we can be more accurate than using the automatic model. So if you have this information, please use this option to enter it. Once this is done, we will see the TTT curve here automatically. It's generated automatically after entering the chemical composition. The options we have now is to export a PDF in case we want to share the TTT curve, and we can save the material file. When we do this, we will get 3 files. First, a general file called TMF that contains the general information for the material. It's just a way to link the material information in the 2 other files. In the TTT file, we will have the diagram, the TTT diagram, and the beaker hardness versus temperature for each phase. In the LOI file, we'll have the flow stress for each phase and a table of coefficients as well. In FORGE or SIMHEAT, what you have to import is the TMF. Importing the TMF will automatically import the 3 files as long as they are in the same directory in your simulation. This is the main file, the TMF. Okay, moving on. When we create our TTT curves, the model will also generate an automatically the CCT curve, continuous cooling temperature diagram transformation. Here to improve the CCT curve, we should enter the austenized temperature that we are using. That's the only parameter we use to optimize the CCT curve. Okay. Another functionality of this tool is to import an experimental CCT curve. If we have a CCT curve that we have obtained with any sensors, whatever method you use, we can import it in this tool using the CCT diagram option. Once you have imported the CCT diagram, of course, you first should have imported the TTT curve. You will see 2 curves in the CCT section. The aimed curve or experimental curve will be here in gray, and the automatically generated curve from the TTT information you enter will be in color. We have an option here to launch an optimization that will optimize the TTT information that generated the automatic curve to approximate the color curve to the gray curve as much as possible. It's a way to optimize your TTT data using an experimental CCT curve. Once you click in Launch Optimization, you will be asked to enter advanced options if you want. If you're going to get into this type of optimization, please contact us and we will give you details about these parameters if needed. They are advanced, so they are not always needed to run the optimization. Once this is done, you will have the possibility to save the new material with the optimized TTT curve. And then you can import it in our software. Another functionality for the diagram generator tool is the TTL Diagram. We've been talking about the TTT CCT section. If you click down here in TTL Diagram, you will open a new interface. These diagrams are used to improve the TTT data when we have high heating rate. This will give us the possibility to enter variations in the AC1 and AC3. Those are the characteristic temperatures of the TTT diagrams as function of the heating rate. I'm going to show the options we have in the TTL diagrams now. We will be able to choose between these 3 options: equilibrium, TTL diagram, or very high heating rate. Equilibrium is the default temperature, is the one we get by the automatic model. We won't be able to enter anything if we choose this option. Choosing TTT diagram will show us an interface like this. We will be able to enter different AC1 and AC3s for different heating rates. We can enter a lot of them and import them from Excel if needed. Then for our welding simulations, we use this option, the very high heating rates. We use two coefficients. It's a Leblon type model, and this is the equation we use. If for welding simulations, please contact us and we will give you more details about it. Okay. With this mentioned, we can move on for the specific characteristics of the quenching and austenitization templates. For this type of simulation, the first thing to consider is the phase transformation data. We will want to have this information. That's what we have been talking about, the TTP curves and how to generate this information in FORGE. To import this, we just need to import a material file with TTT data on it. If we do that, we will automatically get results for the different phases. To obtain this data, we have three options: the TTT CCT diagram generator, if we have microalloyed steel. We can also use any experimental data we have or any data we find in the literature if we consider is accurate enough. We can import any curve in FORGE. We will help you to adapt this information to the material file, but you can use the default materials as templates. A third option is GEMAT Pro. This material generator software has a direct export to FORGE, and it has different modules, as you can see here. We can export phase transformation for steel, titanium, cobalt, and nickel alloys. That's the current functionalities. It implies an additional price if you don't have the software. Please contact us for details or contact them directly. GEMAT Pro sent the software for details. This is just an example for two different temperatures. We have stress versus strain for the different phases. It has several advantages. For example, large domain of deformation from 0 to 4 normally. These are just examples. So it has a large domain of strain rates too. We can move from a small deformation to large deformation with this material file. Okay. Once we have made clear how to use TTT data, next thing that is important in quenching is the HTC, or heat transfer coefficient. It has a huge impact on the final microstructure. And normally we use constant values, but these HTCs are normally depending in a lot of things: quenching area, orientation of the part, material, surface temperature. We don't have to enter constant values. It's possible in FORGE to enter, for example, in this case here, we are showing the HTC between water and the C55 material. As you see, the HTC on the y-axis is not constant at all. It depends on the surface temperature on the part. If we enter a constant value, we will not get results as accurate as we will get if we enter this variable value. I'm going to show how to do this in FORGE in the next slide. When we try to import the HTC for the ambient media, we'll see a lot of new options in FORGE 3.0. Most of them are constant values, but for example, heat transfer for humidity conditions, we have the example here. This is what we will be importing. I'm going to dedicate some time to talk about these two templates: the heat transfer with water dependent on surface temperature and heat transfer with water dependent on surface temperature, adding a switch function. Those two, I consider that they are really important, so I'm going to explain them in detail. First, this is an example for HTC versus surface temperature curve. Here, what we have to do is edit the HTC file that we have in our simulation folder with a text editor. There, we can add a point per point load. This is how it looks. You can use the template again. It's called heat transfer with water dependent on surface temperature. You can use that and then modify the points according to the curve you have. Otherwise, this is the block you have to add to the HTC file. If you have problems adding it, please contact us to our support email and we will assist you. But I want to show that it's possible to add HTC dependent on surface temperature. It's actually quite easy, as long as you have the information or the characteristic curve. Another option would be adding an additional block to that file previously shown, where we add an additional condition. In this case, we have a part that is going to be in the water first, and then it's going to be in the air. To add this effect, we can change the HTC based on the C coordinate. This is another function. Again, you have the template in the default files. We are adding a dependency for the alpha external. This is the HTC for ambient media, using this value 3. 3 means is depending on the C coordinate. You have the different options here from 1 to 5. Then we have the value that will trigger the switch. This is the C coordinate 0. Once we move over that coordinate, we will move from condition 1 to condition 2. The HTC will be 10 once we pass this coordinate. This way we can simulate the quenching in the water and then the cooling in the air. If you want to visualize the emissivity and the HTC with ambient media, what we call alpha external, you can add a user variable called alpha x and epsilon. It's in the miscellaneous folder. Please see the user variable webinar we did last time for details on how to do this. But it's possible to visualize how this coefficient is doing, thanks to this user variable. Okay. Another option with a user variable, a new function now, it's add quenching with sprays. I'm not going to get into detail because it's a little complex, but it will add in the user variable. Again, please review the previous webinar for details on this. Will allow us to simulate these 2 columns of sprays, for example, to simulate the quenching with them. You can experiment with this and let us know if you have any issues with it. Also, finally, my final comment about HTCs is that now we have a new database for a specific quenching medias. We have created this with the help of Hangtom here. It will be a new category for the quenchants, and you can see details about how to get more information about them in there, and you can see the curves for the quenching. Okay, really useful. You can try to find your solution here or find a similar one. We are adding new individuals to these quenchants with each version. Okay, that's all for the HTC. Now I would like to talk about the anisotropic meshing. This meshing will add an anisotropic meshing in the external surface to reduce enormously the number of elements in our part and keep a fine mesh in that area. To do this, we have to go to meshing and anisotropy. This is only meant for quenching and carburizing all these heat treatment templates. So you won't see it in every template. Once you have a volume mesh, you can go to this section and enter first the depth of the meshing. 2 in this case means there will be 2 millimeters there. the number of layers, you have the options here: very fine would be 20, fine 10, average 5, coarse 3. I'm showing an example here with a very fine layers. As you see, we'll have really thin triangles. They are anisotropic, and this will keep a fine mesh in the external surface, reducing the number of nodes. This means the simulation will run a lot faster. To launch this anisotropic meshing, we have to use processors in our computer. So you will have to enter the number of processors and use as many as you use to launch your simulations. That's what I recommend. Once we launch it, we will see a computational window running the anisotropic meshing. And this is the constant value. This is the value inside. In this case, in this one I ran, it was 1.65. Also, we have to add a set to specify the external surface where we want to apply this. Sometimes it's not in the whole external surface and it's only in a localized area. You can use a set to specify this area. You have an example here. This is a standard isotropic mesh. You'll see the equilateral triangles there, and we have more than 80,000 nodes. For the same part, we run the specific anisotropic mesh. You see the anisotropic triangles pointing in the anisotropic direction, and you'll see the amount of nodes is extremely lower. We were able to speed up the simulation enormously. Okay, that's all for quenching. Now I'm going to give a quick note about carburizing. It's a complex topic, so I won't be able to get into a lot of detail, but I'm going to give the main tips you need to know to run a simulation. Carburizing, what we're trying to achieve here is to increase the carbon rate in the external surface in order to increase the hardness. To do this, we'll need to add a diffusion block in the material file. We have to open the TMS file and add the diffusion block. It looks like this. You can find the template in the material data folder in the installation folder. You can use the default file. It's called Diffusion Carbon and Steel TPT. You can go to this file and copy paste this block just as you see it here in your simulation, in your material file. Okay, this is for the material file. Now, there's a specific template for carburizing. It's called 3D chemical element diffusion. Please use this when you want to run a carburizing simulation. Okay, once we have done those two things, modify the material file and import the new template, the main difference with other simulations is going to be this, the chemical element diffusion. It's in the billet and in properties. Here we'll have three parameters to modify. First, the boundary condition. I will talk about the 4 different options we have. We can start with perfect exchange for our first simulations. Then the constant chemical element concentration. This is the initial carbon content in the part. It has to match the material file. Otherwise, the simulation will crash. So please make sure the carbon content is the same as in your material file. Next, we have the carbon content in the atmosphere. It has to be constant. So if you are changing this content, normally carburizings have different phases. In this case, we started with 0.8 in the atmosphere, but we moved to 0.6 after a certain time. This means you have to run 2 carburizings. If you are going to modify this value, the carbon content in the atmosphere, you have to run 1 simulation per carbon content. Okay, and then for the boundary conditions, we have 4. I don't have time to enter in details. You can use perfect exchange. It uses a direct edge condition. What it does is it takes the atmosphere chemical potential, it imposes this value on the external surface directly. You can use exchange with resistivity too. And this is normally done for mixed nitrogen carbon monoxide atmosphere. I don't have time to get into details here. If you use this, a good starting value is 1.5. This is all the quick tips I want to give. Normally we'll use perfect exchange or exchange with resistivity. Perfect exchange doesn't require any values, and exchange with resistivity, normally a typical value is 1.5. For details, please contact us or schedule a training in Carburizing. Okay, next, here, a couple of tips after we have the results. If we want to run posterior simulations, we have to do a couple of things. If we are going to run a quenching, we won't be using an element diffusion template anymore. So in order to transfer the carbon rate results, what we have to do in the quenching simulation is to import this user variable called transfer carbon. We have to do this before launching the quenching. So you can import the result from the carburizing in the quenching, and then just add this transfer carbon. With this, you will keep the results you obtained in the carburizing simulations. If you don't add this user variable, you won't be able to see the different carbon rate you calculated in the carburizing. So please make sure you import the user variable. Another detail, if we are going to run a second carburizing right after the first carburizing, I just want to emphasize that you don't have to fill the constant chemical element we entered before. Here, we started with the initial carbon rate in the material file. If you do that, you will be overreading the results. So you don't want to enter that in the second carburizing. You want to leave this box blank, so you import the results from the previous simulation. You don't want to replace them with a constant value. So final note for carburizing, carbon diffusion and phase transformation, you can combine both in the same material file and in the same simulation. You have an example where we have the three phases here and the hardness. We increased the carbon rate in the external surface, and we still have this transformation. This is possible. And we have a new tutorial dedicated to carburizing in the online help. Please check it out. It's in tutorial 3D carburizing. You'll find all the steps in there. Finally, we're going to talk a little about tempering. Tempering is normally done to decrease the residual stress from the previous heat treatments or to improve the compromise between hardness and ductility. It's normally a heating, isothermal holding between these temperatures or these temperatures, depending on what we want to achieve, and then a cooling. The mathematical model we use in FORGE or SIMHEAT, and it's going to be used to calculate the hardness evolution, and what we need is the chemical composition of the steel, tempering temperature, and tempering time. This will be a new simulation, and we will get, as I said, the hardness evolution, just entering these three parameters. What is special about tempering is the material files. Before running a tempering, you have to use one of these, let's say, material files templates. They are located in this folder, material tempering, and you have to select one of them depending on the simulations you have run before. Once you have selected one of them, you will have to modify the material file. We have three types of files. Martensite only if we want to simulate a tempering with 100% martensite in the material. We have after quenching for a simulation run after quenching. It's to take into account the phase transformation. Also, we have the after carburizing quenching. And this will take into account the phase transformation and the carbon rate. Once you have chosen the proper material file template, you can modify it with a text editor. There, you will have to enter the chemical composition, then the grain size, and finally, there's another block calculating the hardness. All you have to do is modify this hard unit value depending on the units you want to obtain. Once you have entered that, you can launch the simulation. And as any other heat treatment simulation, you have to enter the tempering temperature and the tempering time. That's all. The main result we're going to check in these simulations is the hardness. We're going to see how the hardness changes. This is an example. This is all I wanted to talk about today. I have only shown some, I haven't been able to get into detail. Heat treatment is a complex topic and it's a vast topic too. There's a lot of information. If you want to get into more details or talk about your specific simulations, get to know how to optimize those, you can contact us to schedule an online training about heat treatments exclusively. We will customize it to your own processes. Other than that, again, as I said in all the webinars, remember that we have the online help. In this case, we have tutorials for carburizing and quenching. There's nothing for tempering. Just main features are the material files. That's what you have to modify. And also the reference documentation. We have the metallurgy document with a lot of technical information about what I just mentioned. So this is all for today. Thank you, everybody, for your attention. And I will answer any questions now if you have it.
I have one question.
Oh, there we go. Yeah, go ahead, Joshua. We'll see if it works pretty well. Otherwise, we'll ask you to use the chat. But go ahead. Okay,
sounds good. I was just wondering, I noticed that you can do carburizing on here, so you're doing the diffusion of carbon. Can you also do other elements?
We are working on adding nitrogen to this element. At this point, the model that we have tested the most is carbon. We can do other elements. You have to contact us with details on what you want to achieve and what you want to simulate, and we will give you an answer. We need more details to answer that question, but yes, it's possible to simulate other elements.
Perfect. Thank you.
Yeah, you're welcome.
Any other question at this point? Okay. So thank you again, Professor Sergio, for this excellent presentation. We will also update training in our website, in the training portfolio. For now, we still have a on-site, what we call the corporate training on specific topics. Next couple of weeks, we will update that. Given the situation with COVID-19, we will focus on online training only. So as Sergio said, we provide on-demand, online training. So we'll customize the training to your needs, but we also want to have, again, corporate online training, which means that we select a topic that, again, is most likely to interest you. And anybody from any company can sign up for that and then join the training, okay? So we're still finalizing the program, but we'll have it ready in about 2 weeks, okay? With that being said, again, thank you very much for joining this morning. we have recorded this webinar, all right, like the others. You'll have it available in our member area. You'll receive an email when it's available, probably on Monday. If you haven't signed up yet for a member area, please do so. Just click on member area and sign up on our website. Our website is www.transvalorusa.com. And then we will accept you shortly after so that you can enter and check all the other webinars. So five webinars we've done before that one being the sixth, are all available in this area, plus a lot of other short videos and tools to make your life easier. We'll still continue this free webinar series with 2 weeks in between. So the next one will be in 2 weeks. I think we're gonna keep this pace until the end of June. So 2 more webinars in June, I think, and after we'll probably switch to once a month. Yeah? It's always gonna be on Friday at 10 a.m. Central Time. Till then, thank you very much all for joining today, and you all have an excellent weekend, and talk to you soon. Thank you very much. Bye.